Hello everyone, today I'm going to go through a technique called digit DP, which is not very well known as one of the DP techniques, but it's very useful. As we'll come to see, it's very often used in the BIO. But before we get onto the BIO, I want to go through two example questions, show you how to use digit DP, and then we'll finally move on to BIO 2019 question 3, which I think is called parking. Nope, not parking, sorry, blockchain. So, let's start out with what digit DP is. So, what is digit DP? Not PP, what the hell? Okay, what is digit DP? So, first, what is DP? That's solving questions with overlapping subproblems. Formally. More informally, it's more like, can we count, in this case count, how many ways there are of building up a kind of structure or a solution to a question based on smaller solutions of the same question. So in digit DP, what we want to do is, we want to build numbers based upon their length and perhaps other info. So what we're going to be doing is we're going to be answering questions about numbers based upon smaller versions of numbers that are solutions to the question that we're asking. So let's go through an example, which is, I'll go through the simpler example first and then we'll do the more complicated example afterwards. So this question doesn't have any inputs. The question is simply, how many numbers exist that satisfy the following? So the condition is that there must exist an index I such that if you take the number, let's call it x, and we take each digit of the number up to I, then the concatenation of all of these digits is increasing strictly, or the sequence of digits is strictly increasing. And if we take the digits from I all the way to the end of the number, then it's decreasing strictly. Let's go through a few examples. For example, 1, 2, 3, 2, 1, that is increasing because we can choose I equals 2 if we zero index. The 1, 2, 3 is increasing and 3, 2, 1 is decreasing, both strictly. If we had 1, 2, 3, 2, 2, well, this is not strict no matter what we choose, so that's not going to work because it needs to be strict. So the question is, how many numbers of any length exist that satisfy this condition? Okay, so let's think. What is the largest number I can think of that will satisfy this condition? Well, since these digits can't repeat, the longest increasing section we can have is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then it has to be decreasing, so we can do this. How many digits does this have? Can you count? 9, 10, 11, 12, 13, 14, 15, 16, 17. So we have 17 digits. This is a very good clue. Now the number of digits we have is not very big, it's only 17, so we could have some DP that's honestly not very efficient, but it will be good enough to solve the question because we only have 17 digits. So now let's start to think about how we can build up solutions to this question using smaller numbers. So let's think about how this question is defined. We'll write out these numbers. So let's say we currently have these numbers up to xn minus 1, and we now want to choose what xn is. How can we choose what xn is? Well, what information do we need about this number so far? Well, we need to know what this is. Firstly, we need to know what xn minus 1 is, because this xn, it has to be more than this number if we're currently increasing, but it has to be less than this number if we're meant to be decreasing. So we have to know what this number is either way to be able to begin answering the question, to be able to choose xn. We also need to know, are we currently increasing or decreasing? Because this question can be rephrased as follows. We have one section of the number which is increasing, which is this section, and another section which is decreasing, which overlaps that one number, which is that section. Okay, so we know that these two things have to be in our state, in our DP state. So now let's try and write out this DP state more formally. So we require the current length of the number, because we need to know at the end, we need to be able to gather up all the numbers of the different lengths. Okay, we need to know what is happening. Sorry, I've just got this tablet recently, so I'm getting used to it. Okay, next we need to know the last digit of the number that we added. And then we also need to know, are we increasing or decreasing in this current section of the number? Okay, that's our state. Now let's think of what are the base cases that we know. Which states do we know the answer for? Well, we know that when the length is 0 and the last digit was 0 and we are increasing, we know that there's one number, or there's one case where this is true. And the reason I've chosen these is because, well, firstly, this base case is meant to represent the number. Is meant to represent the empty number, or in fact, it would be more precise to write epsilon, but yeah, we'll write epsilon. Okay. We know that this has no length. We don't know what the digit is, so we're going to have to choose this arbitrarily. And we start off in the increasing section because the increasing section is on the left of the decreasing section. Now, since we're increasing, we know that whatever digit we choose is going to set a restriction on our number that the first digit has to be greater than it. So we're just going to choose 0 so that we can choose any number from 1 to 9 to start off the number. Okay, so that's our base case. Now let's consider the transitions. Well, first we need to pick a number D. We need to pick a digit D to add onto the number. Now this digit D must be less than the last digit if we're decreasing, and it has to be more than the last digit if we're increasing. Now, once we've picked this digit D, we can now transition to the next state, which will be when len goes to len plus 1, because we're adding on a digit. The last digit will become D, and the the flag, right? So whether we're increasing or decreasing, if we're in an increasing section, we can either stay increasing or we can begin our decreasing section. But if we're currently decreasing, then we must stay decreasing. Okay, so those are the transitions. Now we just need to locate where the answers are, or where the answer is. The answer is going to be the sum of, let me write that better. The sum of, that wasn't very much better, but anyway. The DP states where we've got a certain length L, and the last digit can be anything from 0 to 9, it doesn't matter what the last digit is, and our flag is off. So we're in a decreasing section. That's for all I from 0 to infinity L. But can we make a better upper bound? Because unfortunately we cannot compute infinity sums on a computer. What is this bound going to be? Well, we found out earlier that the maximum length number we can have is 17 digits. So let's just say that this is 17. Cool. So now let's code it. And in fact, I already did one attempt at this recording, but it wasn't good, so I just scrapped it. So I'm just going to edit this code I have right now really quickly to fit the requirements of the question, which is that we require that we have a length up to 17, and we can have any digit and any boolean. And then let me just fix this. I'll come back to this at the end, I'll rewrite that bit. Okay, so let's go through this code. So first, I like to write using LL equals long, since just to be safe really, because our numbers can have up to 17 digits, we know that for sure guaranteed upper bound, which is definitely going to be way bigger than the actual result, is 10 to the 18, because there's only that many numbers in that range anyway. Or 10 to the 19 perhaps, but a long will fit anyway. Let's think, is that 10 to the, well no, 10 to the 18, yeah. Okay. No, we don't have an input this time anymore. So we just need to clear the DP, because sometimes when you create these arrays outside the function it has random numbers in it, I don't know why, but mem sets it. Base cases. So again, our base case is when our length is 0, the last digit is 0, and we're currently increasing. And I've just arbitrarily chosen 0 to be increasing and 1 to be decreasing. So now we need to go through the transitions. So we're going from every len up to L, and we're transitioning forward. For any last digit and for any flag. Now we need to go through all the digits that we can possibly choose. So, if flag is 1, that means we're now in an increasing section. So the digit we choose cannot be less than or equal to the previous one. If it is, then we can continue and we just don't do any transitioning. And similarly, if we're in the decreasing section, then the digit cannot be more than or equal to the last one. So now, as I said earlier, if we're currently in the increasing section, we can either stay in the increasing section or we can change to the decreasing section. But if we're currently in the decreasing section, all we can do is decrease. So, what I've done here is I've said that either way we can stay in the same section. So len goes to len plus 1, last digit becomes D, and the F stays the same. Or, if we're currently in the increasing section, then we can swap to the decreasing section. So now, to get the answer, we will store it here, and we will go through all the different possible lengths. In fact, that should be 18. Whoops. So let's do that. And can we have 18? Yes, we can. So we do include that this time. And what we're adding is the length, that length, sure. And we need it to be, the last digit can be anything. So we can have last digit from 0 up to 9. And the flag must be, let's see if you can figure out what the flag must be. Must be 1. Can't be 0. The reason for that is, if we're at 0, we are double counting. Sorry, if we allowed both 0 and 1, we're double counting. Because here we're considering switching to the decreasing section at every point, if we then, at the end, say that, you know, when f is 0 it also counts, then we're now double counting the same thing. But if we just have 1, then we're not going to double count anything. Okay, cool. So now we can print out the sum. Let's double check this is all right. Looks good to me. Let's test it out and see what the result is. Best way to check that is by putting it on Google, seeing if it comes up with anything. And I don't know what's going on. I'm just gonna assume it's correct, to be honest. I mean, it looks pretty correct to me, I guess. And actually, I did have this program that we can make it go from 0 up to, but it can't go up to the, so we can't actually check whether it's right or not, but we can just hope that it is. And if it's not, then someone correct me, but I'm fairly certain that's correct. Okay, cool, so that's the first question done. Now let's move on to the next question. Move my mouse to go to a new place. Cool, so next question. This is going to be a bit harder than the last one. The last one was kind of a warm-up. The question is, how many numbers in the range LR are weekly increasing, where L and R are given to you and they can be between 1 and 10 to the 18. For example, 1225 is fine, 13577 is fine, but 1352 is not fine. Cool. Pretty simple question, and at first glance you would think it would be easier than the first one because now it can only be increasing, but the fact that we have to go between L and R makes it very difficult. But luckily I have a solution for you. So what we can do is, well, first let's think about how we're going to build bigger numbers out of smaller ones. So now what is the information we need? So let's say we have these numbers here that are unknown to us, and we now need to choose what xn is. What information do we need? Well, firstly, our number has to be weekly increasing, so we have to know what this is. But there's also more information we need to know. We need to know whether the digit we're choosing needs to be higher than the one L. So for example, let's say L is 123, and let's say that x so far is 1, 2, and we've got yet to decide what this number is going to be. Well, since these 1 and 2 are the same, we know that the digit we choose has to be more than or equal to 3. So not only is it more than or equal to 2, which is the previous one, but it's also more than or equal to 3. Okay, I mean, let's think of another example now. Let's say we had L is 1, 2, 3, but X is 1, 5 something. Well, in this case, it doesn't matter what we choose here. We can choose 0, even though that's technically not correct because it's not increasing. But hypothetically, it doesn't matter what this next number is. It's always going to be more than L. Sorry. So in this case, the only restriction we have is that D is more than or equal to 5. Okay, let's do some more examples now. But what if... Whoops. Bruh, it's like impossible. You know what? I'll just put this D over here. Don't have to delete it, to be honest. Okay. Right. Now let's say L is 1, 2, 3. And X is 1, 2. Blank. Blank. Okay, hang on. If our number's 4 digits long, then it doesn't matter what we choose, because like even if we choose a 2 here, I mean, it's still going to be more than L, because whatever number we pick here, this is 4 digits, that's 3 digits. So, I mean, looking at this, the information we need to know is what is well, the information we need to know from the rest of the number is, we'll have this flag, we'll call this F1, is does the next digit, xn, need to be greater than or equal to the length digit of L. So for example, here the length is 2. Does the next digit need to be more than this digit in L? And that's a flag that we need as part of our DP state so that we can inform our decision about choosing the next D. Okay, and then similarly, we also need to know F2, does the next digit we're choosing need to be less than or equal to R len? And you can convince yourself that, or you can try and kind of find the different cases of where this might need to be true. So now we know some of the cases where it needs to be true. Let's think about what the hell? Sorry about that. Let's think about how these flags are going to transition. So, if the number we currently have, if the flag is on, how do we know whether the flag is going to be on for the next state? Well, the flag is going to stay on only if we choose the number that is the same as the one in L. If we choose any number more than the one in L, then all the numbers after that, it doesn't matter what they are because we're now bigger than L. So we know that F1 will be true, and I'll write F1 prime will be true if and only if F1 is true and the digit that we chose is equal to the digit in L. And, oh whoops, sorry. Let's see if I can take that, paste it. Oh, look at me go. Look at me. What's that? I don't know what that is. Oh, I'm back here again. Anyway, similarly, F2 will be true if F2 is true and the digit is the same as... How come I can delete it now? Anyway, whatever. That D can live. The F2 prime will be true if F2 is true and the digit we choose is R len. Okay, cool. So now we kind of have an idea of how our transitions are working, but now let's formally write down the states and transitions. So what states do we need? Sorry, what do we need in our state? We need, firstly, something which I'm going to leave blank for later, because I haven't gone through that yet. We need the current length of the number that we've built so far. so that we can gather the answers at the end. We also need to know the last digit. And then we need those two flags F1 and F2. So the transitions, well, we know that the length is going to go to length plus 1. How did I spell that? Length plus 1. The last digit will become D, whichever D we choose. F1 and F2, this is F1 and D is ln, as I said before. And F2 and the digit is ln. Okay, cool. Okay, so I'll leave that other one blank for now because we don't know what that is yet. Now let's think about the base cases. So which states do we know the value of? Well, we know that when the length is 0, when the last digit is... Well, last time we chose 0 because our numbers were strictly increasing. So this time we're going to choose 1 because our numbers are weakly increasing and they can't start with 0. F1 and F2. Okay, now this is interesting bit. How do we decide what F1 and F2 are? Is there a single base case that's going to work for all the different DP states? Well, no. Because F1 and F2 depend on the target length of the number that we're going for. So what we need now is to alter our state that we have and add in the target length, which does not change between transitions, but will only change the base cases. Now we know that when the target length is going to be somewhere between the lengths of the numbers, and the target length is what influences what F1 and F2 are. So if the target length is equal to the size of the left, then F1 is true. Similarly for R, if the target length is the size of R, then F2 is true. Okay, cool. Now we know the base, we need the states, the transitions, the bases. Now we need to see where our answers are coming, or where the answer is coming from. The answer will be the sum of dp. Now, let's see, the target length, that's going to be any length between the length of L and, I'll just say like target length TL and the length of R. The length has to equal this. The length has to be the same as the target length. The last digit, doesn't matter what the last digit is, so anything between 0 and 9. And now the flag 1 and flag 2. The flag 1 and flag 2, well, they can be anything, it doesn't matter. So we can have 0 or 1, 0 or 1. And we just sum up all of these for all different values of TL. And all different values of D. Cool! Let's zoom out. So now we know what we're doing. This is a good way to approach any question, by the way, writing any DP question, writing out states, transitions, bases, answers. It just really helps. So now let's go into the code. So increasing. How many numbers are increasing in the range LR? So here's our DP table. So the target length of the number can only go up to 18 because of the bounds of the inputs. And the current length can only go up to the target length. The last digit can be anywhere between 0 and 9, and then the flag 1 and flag 2 are just booleans. Again, we're using long because 10 to the 18 is the maximum answer, upper bound possible. So first we take the inputs and convert them to strings, just so we can nab the digits pretty easily and get the sizes of the numbers as well. Okay, so now we need to fill in all our base cases. So this len is the target len, so I should probably replace these with target len. So we're going to set the dp of the target length, where the current length is 0 and the last digit was 1, for reasons I explained earlier. And the first flag is true if our target length is the same as the length of L, and the second flag is true if the target length is the same as the length of R, for reasons I explained before. Now the transitions, so this bit looks really funny because there's 5 for loops stacked on top of each other. Oh wait, 6. But the thing about digidp is that because the length of the number can only go up to 18 and we only have 10 digits to choose from, I mean, we can have 5, 6 for loops and it will still run very, very quickly. So basically we're just going through all the possible different states here in the first 5. So now we need to do the transitions for each of the states. So the lowest digit can be is going to be either the last digit, is going to be at least the last digit, but if the F1 is on, then it has to be at least whatever digit is in SL. And for the upper bound of D, the upper bound is 9 normally, it could be anything. But if flag 2 is on, then we know it has to be less than or equal to the corresponding digit in R. And then what we can do is we can go through all the possible different digits and perform these transitions where we're changing F1 and F2 like this, as I explained earlier on the whiteboard. Then at the end, we go through all the DP entries which have an answer that we need. So all the target lengths between SL and SR, dot size, all the different last digits, all the different flags, and we add them all up. Get our answer, let's run the code and see what we get. So I have a brute force solution ready to test as well, so I will choose a big range but not that big. So let's do 1, 2, 3, 9, 6 up to 8, 2, 7, 4, 6, 9. We get 4055. Now let's put this in here, and if it doesn't work I have to restart the recording. If it does work I'll be happy. Yeah, 4055. Okay, so now that that works, for funsies, let's time how long it takes for the highest possible inputs if we use chrono to time. Okay. Oh, I wrote T1 twice. So now let's just write 1 up to 1. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh! I forgot. Because the length, technically, that's 19 digits. This needs to be 20. Because the length can go up to 20. Silly, silly me, silly, silly me. Okay, cool. Good thing I tested that, so I don't have to correct it in my comments. Okay, let's do it. There we go. So less than a second. There we go. So we can that would pass. I'm sure there's optimizations you can make. In fact, one optimization that is very easy to make is that we have this extra dimension in the DP, which is for the target length, because we need different base cases depending on the length. But since the base cases are the same for all lengths that are strictly greater than L and less than R, both flags would be 0 for all lengths between 2 and 18 in this case. We can run one of the DPs for those two base cases, one for one being on, one being off, and so we can just run the DPs only for the 4 different possible cases. So really now we only have 4 dimensions instead of 20. But for a question like this, where the input is limited by the size of a long, you can afford to lose some speed by having extra dimensions. But hopefully you understood that, because now we're going to get onto the bio question, which I now need to read, because I haven't actually fully read it. I just saw it and I thought, let's make a video on DigitDP, and I'll see if we can use DigitDP to solve it. And I'll walk through my thought process while I'm reading the question as well. Cool. Let's get my tablet pen out. Let's read it. So, 2019, question 3, blockchain. Okay, so treasures blocks. Okay, pretty simple task description. Okay, yeah, so the reason I chose this question for this video is because I saw that it said give the number of possible blockchains that begin with something something, and the fact that L is so small, I just thought DigitDP. Cool. So what does DigitDP mean? Well, a digit is just a single character that's usually 0 to 9 and base 10, but I mean we can make it 0 to 20 in the alphabet for this question, 0 to 19. Okay, so let's think about this question is asking. Hello, you may have noticed I've changed clothes and it's later in the day. That's because I went to get food, and the first time I did the question, there was more time of me thinking than me explaining. So I've come back with a solution, and I'm ready to explain my thought process and how I got there. So first we need to think, how can we build larger blockchains out of smaller ones? What information do we need? Well, firstly, we need to know which blocks have we already used. And because of this, my idea was to use a bit mask. Basically, this is just a sequence of bits like this, where 1 means that we've used the number, 0 means that we haven't used the number, and I, the index of the bit, tells us which number I'm talking about. So we also want to know the following information. So first, let's imagine that the question is you can't have let's say you can't have 2 characters that are alphabetically increasing. Well, the way we would do this is, let's just imagine we had like ZF, right? Which of these characters is important for us to know whether the next character we add is going to mess up the condition or not? Well, we only need to look at the F, right? Because the F is smaller than the Z, we only need to consider using the F. We know that if we put any letter greater than F, we're going to fail. And if you put any letter smaller than F, we're fine. But every time we put a letter smaller than F, we then need to update which letter is the lower bound for the ones that we're adding. So now let's think about how we're going to apply this principle to blockchain. So let's say we have DGE. Let's say we have DG to begin with, and we're adding, and we're going to see what characters is it safe to add. Well, what we need is, we need the smallest character. I'm going to call this C. The smallest character, such that if the one we're adding is more than that, we fail. So we only need the smallest one because this is a greater than condition. So we're only interested in the smallest character, right? But how do we find and update C? Well, C is going to change only if we add a character that is more than the smallest one. So let's say B is the smallest character. So in this case, B would be D. And whenever we put in a character D that's more than the smallest one, it is now a candidate for C. So that sounds very confusing, but I'll give an example. So for example, let's say we had D, and then G, and then E. So right now, C is equal to the smallest character such that if D is more than C, we fail, which if we put anything more than an E, we're going to fail. B is the smallest one, so D. So right now, it's impossible to lower down C any further, so I'm going to put an A in. So now, how do these values update? Well, C is still going to stay the same, because if you put any letter more than E, we fail. But B is now going to become A. B being A is the smallest character. If we put any character more than A, so let's say C, now this becomes that. Or for example, if we put B, now B becomes the smallest character such that blah blah blah. Because now we can have some character after this more than B, we're going to have A, B, and then that. However, if we have something like... anyway, it can't be more than C because we fail. So we know that if it's more than B, it's going to become that. So all we need to store in our state is B and C and this mask. So we need mask B and C. Now the thing is, if we do something like this, we're going to have 2 to the 19 times 19 squared, which is about 2 times 10 to the 8 states. So this is clearly too much. But the thing is, the smallest character, we can obtain this using the bit mask by just checking what the lowest bit is. So really all we need to store is the mask and C. So now we only have 2 to the 19 times 19 states, which is 1, 2, 3, 4, 5, 6, 7, which is 1 times 10 to the 7. So that's quite a lot better. Now I need to think about the transitions. So we can choose any D that's more than C. Any D that's less than C. So realistically, like worst case, this is the amount of transitions we're making. Which would probably barely fit in the time limit if you implemented it correctly. But what we can do is, let's go to the code now, is use this nice technique where we don't transition from every possible state, we only transition from the states that are needed. And in fact, let me go back to the board just to explain how this is possible. So we know that every DP is represented by some kind of DAG, where each of these nodes is the answer to a subproblem, and the edges tell us how to combine these answers. So since our DP only has one root, it is impossible, or let's not go there, it is guaranteed that when we have that every edge points from a lower depth to a higher depth in terms of the distance from the root. Because if we had, let's say, like another root here, then we couldn't guarantee that the shortest distance to a root here is 1, and it wouldn't be guaranteed that the depths are pointing like that. But since we only have one root, we can say that the topological sorting of this graph is the same as the BFS order, which means that we can maintain the states that we are filling up in a queue and only look at the states in the queue. And this means that the true number of transitions we're making is a lot less than these numbers. And so let's go to our code. So what we're going to do is we're going to define this DP with the number of different possible, or the highest possible bit mask, which is all ones. So 2 to the 19 minus 1, and 20 being the value of C. We can then take in L and P and mem sets our DP things so that they don't have random stuff in them. So now we're going to do this push DP using a queue. So first we need to check whether the prefix they give us is valid or not. And so what we're going to do is we're going to kind of keep track of the mask and the B and C and just simulate the process that I was talking about earlier. So if D is ever more than C, then this blockchain we have right now is already invalid. And so we just return 0. Otherwise, we add this bit to the mask, and we update the value of C, and we update the value of B. And then once we've done all that, we can add this state into the DP and add this into the queue. So now we're going to do our BFS here. So what we do is we just do a standard BFS where we pop off the queue and we get our variables. Now we have low, which says is this, because remember we need to keep track of what B is, but it's not in our state. So we know that B is the lowest on bit in the mask. So we can keep track of a variable called low, which tells us whether we're below the lowest on bit or not. So by default we're below the lowest on bit, but as soon as we reach a bit that is on, we say that we're not below the on bit anymore, and we continue. Okay, cool. If the digit we're choosing is more than C, then it's not valid, as I said earlier. Otherwise, we get the new mask by adding it in, and we update the C depending on whether this value is lower than the old C or not. And then we add to the next DP state, and we use this viz to check whether we've already added it into the stack, because we may have two different states that both lead into the same child state. So I'm just making sure we're not adding it to the queue multiple times by doing this check. And then once we've done this BFS, we can then get the answer by going through all the different all the different C values that are possible, and then just printing it out. So if I run this code, we get, and let's open up the mark scheme. And let's just go with some of these. We'll just try all these 2 markers. 50 milliseconds and 4, that's the right answer. 5508. 50 milliseconds, correct. This one. 53 milliseconds, correct. Don't be fooled by the slow runtime because this is exponential. 0, correct. Yep. Correct. And lastly, this will probably take the longest because it has the highest number. Oof, 300 milliseconds. But I mean, it's comfortably passing. It's correct. So there you go. And so hopefully you get an idea of how digit DP might be used. And I understand that the first question was quite easy, second question was quite a step up, and the third question was a big step up. But hopefully you get the idea, and trust me, you'll get there if you just practice DP. You'll learn to spot these things, and Yeah, hopefully you understood everything. If you have any questions, leave it down in the comments. If you have any requests, leave it in the comments or message me otherwise. But thank you all for watching, and I hope you have a great rest of your day, and I'll see you in the next video.